It's working? Yes, working. Okay, so thank you very much, and thanks very much for the invitation. I've had a really terrific day so far today. So hopefully it's not going to go downhill at this instant. So I'm going to talk about stellar streams, stellar clouds in the Milky Way, formation, properties, and interpretation. But I want to be clear, I think of myself as someone who works on galaxy formation. And so I think of this talk as a talk on galaxy formation, even though I'm only going to talk about one galaxy. And you're used to the locals here tackle this topic rather differently. Is this too loud? I feel like there's feedback. The locals here, is that better? Oh, mic volume. Ah. How about that? How about that? Is that good? Okay. So they tackle this question with vast samples of galaxies spread out throughout the universe. And I instead tackle this question by looking at just one galaxy and instead using vast samples of stars. So as an illustration, this is the endpoint of a simulation of forming not the main component of the Milky Way, just the stellar halo, which is about 1% of the light. So this is about 1% of the light of the galaxy. The scale here is 300 kpc, kiloparsec. And the key point here is, in order to find things, beautiful features like this around the Milky Way, the way you do this is you count stars. And so that's where you get, from counting stars, you can go to very low surface brightness. And you can look at these things in velocity, line of sight speed, and in velocity dispersion. So in other words, what I want to do today, as a start, I'm going to give you a little review about what we've learned from the Milky Way in the last decade or so, studying galaxy formation star by star. Then in the second part, I want to talk about these structures that we found at very low surface brightness around the galaxy and give you some understanding of how these structure forms just in terms of stellar orbits. So very simple physics. And in part 3, I want to talk about if we understand how these structures formed and are connected, can we actually use observations to connect different parts of structures together across the galaxy? And at the end, I want to tell you why you might want to do this, and much larger implications beyond our galaxy. So measuring the full extent and shape and profile of the dark matter halo of our galaxy to better precision than you can do for other galaxies in the universe. Okay, so we're going to start this story about 20 years ago, which of course coincides with when I got into graduate school, so that's my memory. So galaxy formation, the story I was told in the beginning of graduate school, we had already had this paradigm of hierarchical structure formation, which is still there today. And this was developed in the 70s. And the idea being that the matter distribution in the universe is dominated by dark matter, and galaxies form at the center of these dark matter halos that collapse out of the dark matter distribution. And these dark matter halos themselves form hierarchically, with small halos forming first and falling together to form larger halos. And similarly, the galaxies within them, the stellar distributions, falling together to form larger galaxies. And in the 80s, this idea had already been tested and shown to work in many ways. So when I was in graduate school, a lot of the discussion about galaxy formation centered on merging two galaxies. This is an old simulation by Josh Barnes, but it's still beautiful, showing you how you can reproduce some of the observed features of galaxies in the universe, in this case the mice, by simply merging two galaxies together in simulations. And this was a powerful argument to say, yes, this theory of hierarchical structure formation does work. So our picture of the Milky Way when I got into graduate school in the 1990s was basically that the majority of the light in the Milky Way comes from these two major components, the central bulge, and about 10 times more than the central bulge in terms of stellar content is the disk of the galaxy. And this is us sitting partway out in the disk of the galaxy. It was also known at this time that the galaxy seemed to be surrounded by a diffuse stellar halo. It contained only about 1% of the light of the main galaxy, and these stars spread out to actually somewhat unknown distances. There had been some attempts to measure off the fall-off of the density of the stars here. And this is all, of course, sitting inside a dark matter halos that's 10 times more massive and 10 times more extended than the predominant light distribution. And we knew that this galaxy was orbited by of order 10 satellites at that time. So my advisor in graduate school was Lars Hörnquist, and he'd worked with Josh Barnes extensively on grand mergers of galaxies. So he sent me a related but slightly different topic, which was, well, we've done the big guys. How about you look at these little satellites that are orbiting larger galaxies, and let's look at how they evolve. So this is a simulation going back to when I was in graduate school. And I'm going to be showing simulations like this throughout. So just very briefly, you're basically taking an n-body satellite, so the particles in the satellite mutually interact self-consistently just via gravity. And then you've got analytic functions to represent the Milky Way. So they feel the gravitational force from the Milky Way, in particular the tidal forces, which rips the satellite apart. But the Milky Way is represented by analytic functions, and that's the basic method here. So what you can see, the result from my thesis work was basically you take a beautiful ball of stars, and the Milky Way will rip that ball of stars apart. And we sort of knew that that might happen. The fun thing is, what you see coming off from this ball of stars is not the stars wandering randomly into space and getting completely mixed rapidly throughout the halo. Instead, you see these gorgeous streams of stars whose coherence can last for gigayears after the destruction of the satellite. So this was rather fun. What turned out to be even more fun was just how lucky I was that my advisor had sent me this question at this particular time. So I'm sure all you grad students in the audience, your advisors will tell you that getting your PhD is all about hard work and having an incredibly big brain. And you can see that my brain is incredibly big. But I would say that a large part of my success in the field has been luck, in the sense that at the same time that I was simulating dying satellites, the field of discovering dead and dying satellites exploded, precisely because the era of counting stellar catalogs containing hundreds of thousands to millions of stars was really taking off. So, for example, in 1994, a graduate student called Rodrigo Abata in Cambridge, England, England, was doing a thesis on the bulge of the galaxy. This is a sky projection of the bulge. And he was supposed to be looking at the velocity distribution in the bulge. And when he measured the velocity distribution of stars in his field, which was to the south of the bulge here, he found that there was a whole bunch of stars that were not moving at the right speed to be part of the bulge. They were moving at a completely different speed. And it turned out he discovered an entire other galaxy hidden behind the bulge of the Milky Way, which is rather a fun thing to do when you get your PhD. Rodrigo, over the years, it turns out, manages to discover things, luckily, all over the place. So there's something there. He's either extremely lucky, or maybe he's the one who has the extremely big brain. I don't know. Anyway, the point is, in red here, this is an outline of this group of stars that were moving not in the way they should be if they were part of the bulge. And he had discovered the nearest satellite galaxy of the Milky Way. And as you note here, this is not a round object. It's highly distorted and suggestive that it's being torn apart, right? The next big thing that's really made this field explode was the advent of the Sloan Digital Sky Survey, which of course was invented as a galaxy survey, but it turns out the stars in there are incredibly useful too. So Heidi Newberg, this was sort of the first release of what might be going on in the stellar halo. This is a plot. The sun we're at the center. This is our perspective. We're looking out in distance, away from the Milky Way. The points here are stars, not galaxies. So this is not a redshift slice. This instead is a magnitude slice. So, but in other words, the way to think about this is this is where the sun is, and you're looking out in distance to about 45 kiloparsecs away from the center, away from the sun. And the point is, you're looking far beyond the disk of our galaxy. So what you're seeing out here, because of their distances, this has to be part of the stellar halo. And this, in a sense, was the first sort of global view we had of the stellar halo of our own galaxy. Previously, we'd only seen lines of sight here and there. And actually, Nick reminded me today that he was involved in some of this work, the lines of sight. But the great thing that Heidi was able to do with this new data set was make a contiguous map of at least a slice. And the key thing you can see is that it's not smooth, right? There are lumps of things here, right? There are concentrations of stars. So we don't have a smooth ball of stars around our halo. It's lumpy, and it contains lots of structure. Here's another example. I really love this one. This is from the 2-micron all-sky survey, and it's by Steve Majeski. And he was selected giant stars using the peculiar colors in the infrared of M giants. And he's plotting here in basically X versus Y, perpendicular to the galactic plane. He's plotting the distribution of his stars here. And the scale here goes out to maybe 60, 70, 80 kiloparsecs. So here we are. Here's the sun. This vast swath of stuff. These are all disk stars. They're uninteresting. Here's the galactic center. This core, you can see very clearly. This is the core of that Sagittarius dwarf galaxy that Rodrigo had discovered a decade before. It's beyond the center of the galaxy. But then if you look at the halo, this is a slice through his data perpendicular to the disk. I hope you can see by squinting a little bit, there are clear features that look like tidal arms coming up from Sagittarius. So the stunning thing about this image is that Steve had found is tidal arms coming from Sagittarius entirely encircling the galaxy, just very reminiscent of the simulations that I just showed you, right? And lastly, I have to show you another classic slot from the Sloan Digital Sky Survey, this one put together by Volokarov et al. In 2005. And what you have to do, imagine in this image, is that you're lying on your back in the Milky Way galaxy and you're looking overhead at the stars, and you have on special glasses, which means you're not sensitive to stars in the disk, because we're not interested in those right now. You're just looking at stars in the halo. And again, you see there are blank patches in the halo, and there are stars that are in streams. The color coding tells you distance. But the key thing is this is the Sagittarius tidal arm arcing over your head as you're lying down and admiring the view. This was an entirely new stream called the Orphan stream. This was a ring of stars called the Rhinoceros ring that seems to encircle the disk. So again, you're seeing structure, structure, structure. That's the message. Our halo contains all this structure. So if we go on and we summarize where we got to by counting stars around the galaxy, our picture by 2005 had become a little more messy and more detailed than what I'd learned early on in graduate school. First of all, I hadn't mentioned this, but by counting stars, people had figured out that we were a barred spiral galaxy, and our bulge was barred shaped, but not spherical. Then there weren't just a dozen satellites of the Milky Way. At this point, I think we're up to 25, and the number is growing every day, so this number could be out of date. So in just a few years, we doubled the number of satellites of the Milky Way from counting stars and finding lower surface brightness objects. Then the Sagittarius dwarf and the beautiful tidal stream had been discovered, and several other streams. And also, these other collections of what could be debris, clouds of debris had been discovered, things that don't look like streams. And then we're going to talk about those a little more later. But a summary for the Milky Way people, from the theory and observational perspective, we were pretty happy because, I could run a simulation of the destruction of a single satellite. If you add that together, because galaxies form hierarchically, we think that this has happened not once, but many, many times. So we can take not one simulation, but many simulations. Then we can make something that looks like this. This is the image I showed you earlier. The Milky Way disk would just be a tiny portion of this image in the middle, and it would be surrounded by these loops and lumps of stars, remnants of tidal destruction. And this is rather reminiscent of what we actually see around the Milky Way. And so in the end, the local group theorists and observers all very happy, because we basically have a qualitative confirmation of things that cosmologists have been talking about for a few decades now. And I should be a little more exact. I mean, in the last 5-6 years, there have been several papers where you quantitatively compare the structures you see around our galaxy with this sort of simulation, actually mostly this simulation, and you find broad agreement about these structures. So this is a nice confirmation of hierarchical structure formation, part of galaxy formation, on local group scales. And this is what you can get by counting many, many stars. Okay. So that's what I wanted to give you a background of in the first part here. What I want to do now is look at these individual features that I've mentioned, the streams, and in particular these clouds. I've only touched on them so far. I want to talk about how you can understand what you're seeing with very, very simple physics. My favorite type of physics is the simple physics. So first of all, let me show you some of these observations. I've grouped them very simply in two categories. I've already shown you the Sagittarius stream, the Orphan stream. So you've seen what streams look like. They look like streams, right? Astronomers are so great at naming things. Stellar clouds is the other type of debris structure I want to talk about. And here's a few names of things that have been discovered. And the basic idea here, this is actually the same data set, but projected now on an ATOF projection. This is the Sagittarius stream going overhead. That's here. And what Balokarov pointed out here is in the constellation of Hercules and Aquila, he found another overdensity that seemed, doesn't look stream-like. And it also seemed to extend below the disk here. So this is stars that are at a similar distance from us, and they're spread out, in the case of clouds, over vast patches of the sky that cover thousands of square degrees. But instead of being in the form of a stream, they're in the form of a clump or a cloud. Okay. And so these have been discovered in Hercules Aquila. There's one at about 90 kiloparsecs from us, the Pisces overdensity. This is still to be confirmed. There's also a clump around Virgo, which is very complicated and hard to digest at somewhat. And I'm going to come back to this example later. There's another one in the constellation of Triangulum and Andromeda as well. And we're going to talk about those. So in other words, we can broadly separate morphologically. We have streams and we have clouds. And how can we understand those in terms of hierarchical structure formation? For a start, we can look at our simulation. So again, this is the same simulation, which is a superposition of individual simulations of satellite destruction. The individual simulations have different masses, and they're on different orbits. And you end up, unfortunately you can't see this brilliantly. Maybe I should turn the lights down. It was this one, right? Okay. Oh, this is better. Okay, so you end up seeing, from the external view, you end up seeing what look like streams around here. You can sort of see a shell of stars maybe here and see some infalling satellites. If you take the internal view, because of course we're internal to our galaxy, you can see things that look like Sagittarius arcing all the way around our galaxy as viewed from the inside at close by distances. And as you go further out, you still see parts of streams, but you also start to see sort of cloud-like structures that could conceptually be these things like the Hercules Aquila cloud and the Triangulum Andromeda cloud. Okay, you're not allowed to go to sleep, right? But I want to leave this down for a little bit, at least. So you can understand this distinction in debris morphology broadly, just simply in terms of orbit flight type. Because I can look at the simulations, the individual simulations that went together to make that model stellar halo. And what you generally find is, from the internal view, if something looks like a cloud, where the brightest part covers hundreds to thousands of square degrees as a clump, then if you look from the external view, it's clear you've destroyed something on a rather eccentric orbit that comes close to the center of the Milky Way. And these clouds correspond to sprays of debris hanging out at the apocenters of orbits. These have been seen around other galaxies for decades, and these are generally seen as shells, thin shells. But from the internal perspective, as you look out from the center, you see it as a cloud on the sky. And then the streams can be understood broadly as satellites that tend to be on less eccentric orbits. And so the debris is spread more evenly over the orbit, and you see something that looks like the Sagittarius stream entirely encircling the galaxy. So what I want to do, hopefully just for the next 10 minutes or so, is describe this in a little more detail just in terms of orbits, because it turns out you could get a very long way understanding these structures just in terms of understanding very simple orbits, right? And this is work that I've done over the centuries that I've been in astronomy, but in particular this last year, David Handel, a graduate student, has been looking at this with me. So there's a simple plot here, X versus Y. The scales here you can see from 0 to 40 kiloparsecs or so. So the disk of the Milky Way would be sitting here, and these are orbits of stars that definitely take them out into the halo. And we're going to talk about orbits that are circular, so that's easy. That's a circular orbit, right? But you can, if you keep the same energy orbit and you decrease the angular momentum, so the circular orbit would have J over J circ of 1, it would have the same angular momentum as the circular orbit. If you decrease the angular momentum a little bit to 0.8, then the orbit gets more eccentric, right? And it goes in and outside of the circle, right? And if you decrease the angular momentum even more, the orbit gets more eccentric, right? These are very basic, right? But the other thing I should mention, of course, the potential of the galaxy is such that you do see precession among the petals here, so it's not like orbits in the solar system. Now, to start understanding debris, you can look at the shape of the orbits, and the other thing you can look at is the amount of time that a star along this orbit would spend around apocenter. So what we quantified this was we just asked how much time does a star take on this red orbit going between where it crosses the circular orbit here. So it's, in this case, it's 25 kpc. How much time does it spend doing this? And the same thing for the blue orbit. And this is what's plotted here. This is the time, the fraction of orbital time that a particle spends outside the black circle for orbits of different angular momentum. Here's a circular orbit, and here's a purely radial orbit. And you can see that this is pretty flat. So what this is basically saying is, as viewed from closer to the center of the Milky Way, a star on a not quite close to circular orbit spends 50% of its time doing this, and then another 50% doing this. So it travels fairly evenly in angle along the orbit. But if you look at an eccentric orbit, a star spends 50% of its time doing this part of the orbit, and then another 50%, it's going to zoom from one apocenter to the other. This is just another way of saying it's Kepler's third law, that stars or planets or electrons, whatever, on orbits, on eccentric orbits, spend most of their time at apocenter. But the key thing you have to add to this is, now remember, you're an astronomer sitting in the Milky Way and you're looking out at debris structures. The stars are going to spend most of their time over a very small angle here, but steadily over a large angle here, okay? So this tells you in terms of individual stars. The next thing I want to show you is also very simple dynamics. What is it that causes the spreading? It's basically phase mixing, right? But in order to get the spreading, the debris spreads out along the orbit, you can't have all the stars moving at exactly the same rate, because then there'd be no spreading. So we can interpret why stars spread along orbits by saying the debris has a very small spread in orbital energy. And what's plotted here is very simply just the time periods in our potential as a function of j over j circ. So low angular momentum versus high angular momentum for different energy orbits. And what you can see is there's very little dependence on this on angular momentum. So the time periods of orbits with the same energy doesn't depend on angular momentum, but it does depend strongly on energy. So what this means is if you set off a ball of stars with a small variance in angular momentum and energy, over time they're going to sort themselves in energy along the orbit. So here's a ball of stars, well, shortly afterwards, color-coded by energy, and you can see over time the energies remain in the same order. So the spreading of debris along the orbit has to do with the small spread in energy that you've got. And that corresponds to a small difference in orbital time periods. And that's why you get tidal streams. You destroy a ball of stars and you have a range in energies. The second thing that you can look at is, well, what does this range in angular momentum get you in this case? And so what we're plotting here is the angle of precession between different petals of an orbit, and each color corresponds to a different energy. You could just look at R circ of 25, which is the type of orbit we're looking at, this blue line. And this is low angular momentum radial orbits. These are circular orbits, near circular. So you can see there is a big difference in the precession rate among these, meaning the petals don't line up if you look at different orbits with different angular momenta. And what this actually means for the same simulation which I disrupted here is if you color code this now by angular momentum instead of energy, instead of seeing the colors separate and spread along the orbit, this is what causes thickening next to the orbit. Basically, the green, blue, yellow, red particles have different precession rates. So over time, you see a spreading out of the debris perpendicular to the orbit. And the very last thing you need to know before you can explain all types of debris is that this effect of precession of the orbit is more apparent on the more eccentric orbits. So here's the orbit that we started with a minute ago. 5 minutes ago, I showed you a j over j circ 0.1 orbit. If we change the angular momentum by 0.05, then you can see that these start at the same point here. There seems to be a large difference in the position of apocenter relative to the size of these petals. So this precession effect is going to be more obvious for more eccentric orbits. And the precession effect for less eccentric orbits is going to be less obvious, right?
What is the center of the orbit?
The center of the orbit is the center of the galaxy. Okay, but the thing to remember here is, on these scales, I should have said this. Kiloparsecs, you physicists don't always think in kiloparsecs. The sun is 8 kiloparsecs from the center of the galaxy. So we're sitting not quite at the center, but we're definitely viewing this orbit from the inside, right? I think that's the relevant thing. Now, here we go. So I'm technically challenged, so my movies are not in the, so we have a slide, just talk amongst yourselves, blah, blah, blah. Here we go. So let me show you everything that I've said in terms of movies, because these are much more illustrative. This is an external view of a satellite disrupting on an orbit with moderate eccentricity. That's the dot here. The external view is at 25 kpc. This was the circular orbit, and this is slightly more eccentric. So you can see, as I've shown you before, I can make streams of stars. And this is the view from the center of the galaxy. And when you make a stream externally, what you see is, over time, it's going to wrap entirely around the galaxy. Okay? Yeah, sure. So I don't actually know. I'm guessing half a gigayear, maybe. A radial orbital period. Maybe a little less. Maybe 0.3 gigayears or so. Yeah. So you definitely see something that looks stream-like in this view, right? Now let's look at this case. This same thing, but now color-coded by energy, the orbital energy of the stuff falling off. The black is still bound particles. The blue have moved to orbital energies which are more tightly bound to the Milky Way, and these ones have moved to orbital energies that are less tightly bound. And what you should be able to see is that as this object goes past pericenter, it loses mass. But subsequently, the things that are lost organize themselves in terms of orbital energy. So the dark blue particles head towards the end of the tail. The red head towards the end of the tail because they have a larger difference in orbital energy, a larger difference in time periods. So when you look along a stream-like structure, you should see an ordering in orbital energy. Okay. If we now do the same thing, but now the simulation is color-coded by difference in orbital angular momentum, you should see here, over time, it's a little hard to tell because of the mixture, but you should be able to see the red particles and the green particles separate perpendicularly. That's a signature of these orbits having different precession weights. So these tails are thickening slightly because of the difference in precession rates of the orbits. Okay, so that's for stream-like structures. Now we can do the same thing for an object on a much more eccentric orbit. So it's the same object, I think it's a 10 to the 8th solar mass object, on a much more eccentric orbit. And you tend to see, it still looks as if you can see streams here. If I made this in surface brightness, you'd see most of the particles are sitting at apocenter. And in this view, it's quite dramatic. You can see these clouds at apocenter. They're ever so gradually moving because they're different energies, and the apocenters have different energies, have different precessions. And that was the quick, massive ball of stars that zips between the apocenters. That's the still-bound satellite. And the fun thing is, of course, you can see not just one cloud associated with an object, but sometimes you can see 2 or even 3 clouds on opposite sides of the sky. So they're not like streams. These clouds aren't even connected in a way that you can trace in space. But you could conceptually have clouds on opposite sides of the sky that are connected. So let me show you the same thing. But this time this is color-coded by energy difference. Oh no, sorry, I'm showing you the wrong one. Let's come back to that one. Sorry, you're not allowed to see that yet. No, that's I think I've opened the wrong one. Okay, so this one. This one. Okay, this one is color-coded by energy. The eccentric orbit color-coded by energy. Again, you can see that the particles spread along the orbit according to their orbital energies, right? However, the interesting thing is, in the stream, you could look along the stream and see different orbital energies. But in this case, what you tend to see is the orbital energies are sitting on top of each other because all the particles crowd up on top of each other at apocenter. Okay? So when you actually look at this, uh-oh.
What keeps them more or less condensed?
More or less condensed. Oh, because the spread in energy and angular momentum is small, right? So they're close to the original orbit. Now, over time, they should spread out all over the sky. But because you have a small progenitor relative to the parent, the difference in energy and difference in orbital angular momentum is small. Now, if you had a merger between two large systems, the differences in the energy and angular momentum of the orbits that the debris goes on is much larger. So the mixing is faster. Okay. Any other questions? Yeah.
Can you describe these by a continuous probability function? Find a solution for such a function.
Right. So you can, yes, you can look at the distribution in energy and angular momentum. That's going to stay fixed unless you play with the potential. If you play with the potential, you'll scatter it. But you can look at the energy and angular momentum distribution, and then you could apply that to predict what the density distribution is, quite simply. You can do that analytically quite successfully. Yes. Yes.
I mean, what holds this all together? Gravitational?
No. So the satellite is being held together by gravity. The coherence of the streams.
Newton's law of gravity is equal to mv squared over r.
Right.
That is the basic assumption of your calculation.
For the satellite, but once it's unbound, right, they're orbiting the parent galaxy. And they're close together because of their similarities of their orbits, not because of initial conditions, not because of self-gravity in the debris, right?
Yeah, I'm wondering what the forces in your model are.
Right, so the force is Newton's law of gravity between the particles themselves and Newton's law of gravity between the particles and the parent galaxy potential, right?
Okay, and then also there is centrifugal force.
Right. So that comes in naturally as you integrate the orbits, right? You're integrating the orbits in the force law provided by Newton, right? Does that make sense? So you're calculating the gravity self-consistently for the particles, and you're imposing an external field on them.
Dark matter is included in this.
The dark matter is included in the potential. So you're assuming that it's a dark matter halo obeying Newton's law of gravity, mass distribution. Okay?
And then are you going to tell us how this agrees with velocities with observation?
Oh, yes, I am. In 2 hours' time. Was another question over here. It's okay. Okay. But I can also, right, I apologize in the sense this is the first time I've given this talk and I like this stuff. So we might get distracted. I think that's okay. We can just miss out later chunks, right? But I wanted to show you this one more thing, if I can find it. This one, which was the last version. This is the highly eccentric orbit, color-coded by angular momentum difference. So here's the fun thing. Now, if you look at this, you can see very clearly the difference in precession rate really causes the spreading out of the clouds, right? So they're spreading out in energy along the orbit, but when you look across a cloud, you're seeing a difference in angular momentum that's caused by the difference in precession, right? And that's what's causing clouds versus streams. So essentially, the physics is exactly the same, and just by understanding orbits, you can understand the different morphologies of the debris structures. Okay. So, before I go on, any more questions? Okay, let's go back to this. So I have another technical issue. I never know how to start at the right place. We'll get there. All right, so conclusion so far, I'm just trying to tell you that this is just streams and clouds that we observe are just debris dispersal from satellite disruption. So they're the same type of object, but different orbits creates different morphologies. So this, we're done with part 2. So what I wanted to do now is talk about 2 simple projects where we start thinking about what you can tell observationally from looking at debris clouds and debris streams. And in particular, I'm going to concentrate on clouds because streams have been done more historically in the past. So I want to come up with some simple ideas of what you can learn observationally looking at these structures. And we may not get to both of these because I want to tell you about the last part. But let me at least talk about this first part. So the first thing I want to tell you about is a project with Alison Sheffield, who's an observer, and also with a group of other people. But Alison has basically looked at giant stars in the halo of our galaxy that you can select photometrically from the 2 Micron All-Sky survey. And this was actually how this entire wrap of Sagittarius was first made. But she was doing something a little bit different. So here we are in the galaxy. She was looking at a relatively small volume compared to this Sagittarius stream and just taking line-of-sight velocities in this volume. In fact, she didn't look at the whole volume. She was looking at high galactic latitudes, so sort of looking out of the disk up and below and taking line-of-sight velocities in this volume. And this is what her data looked like. So this is basically line-of-sight velocity relative to the sun. And this is a function of angle as you look around in the disk of our galaxy. L is galactic longitude. And the majority of her 1,800 stars seem to follow a sort of sinusoidal distribution. And we can understand these as being members of the galactic disk because they're following on orbits close to the sun in a predictable way. So these majority of these are galactic disk stars. And we were interested in particular of these stars that moved at high velocity along our line of sight relative to the galactic disk. And so we looked at this image and we started seeing patterns. And I'm not saying these are statistically significant, just bear with me. But we thought in particular, it kind of looks like we've got a line of stars here, a sequence of stars here, and maybe this is a sequence of stars here. And I've highlighted them so you can see what we were talking about. And we're not sure that these sequences of stars are real, but we were curious about them. So we went back to the simulations that I'd run and asked, do we ever see sequences of stars like this in our simulations of the halo of which is formed entirely by accretion? So in other words, what we did was we did a synthetic survey of our simulation. So here's the simulation again. We put ourselves at 8 kiloparsecs from the center, and we drew a tiny volume around here. So this is 300 kpc. We're talking about a small volume around the sun. I can't even show it evenly enough. And we're asking, well, what do stars look like here? We're not going to see vast streams and things like that because they're on a different scale. So if I make a plot like the one that I just showed you, so this is velocity along our line of sight relative to the sun as a function of galactic longitude, and then I color code the points that I observe in my simulation according to the satellite from which they came, then we can say, well, look, there's a sequence of red stars that's perhaps reminiscent of these observations. And because this is the simulated universe, I can actually go back and say, well, where did this sequence come from and what does it correspond to? And it turns out that the sequence of red stars correspond to the dark dots here from a simulation of a satellite accreting on a fairly eccentric orbit. The vast majority of the stars along this orbit sit at the apocenter in a sort of cloud. And what we're seeing when we see stars moving at high velocity relative to the sun and they form a sequence is stars moving at this is now in velocity space, stars moving at almost the same velocity streaming through our survey volume. So we call these things pericentric streams. So they're high-speed local star streams, but they're not the same as the stream from Sagittarius in the sense that they're spatially very diffuse. We would not see this as a stream in space. And our interpretation is that they come from, when we see them in the simulations, these local velocity streams come from objects that are dispersing on highly eccentric orbits. And one implication is if you see a local velocity stream like this, it's more than likely, it's very likely to be connected to a big clump of debris, a cloud of debris, somewhere else in the galaxy. So the fun thing we did next was say, okay, well, we have a local velocity stream. Can the observations actually tell us anything more? I mean, this is an interpretation. Can it tell us anything more? And here's, oh, sorry, that was another arrow I forgot. Here's what we came up with. Let's think of these pericentric streams. Here's the sun. Here's our survey volume. And a crude picture of what we're seeing in the simulations is we're seeing the debris streaming past us at high velocity with a single velocity vector. So even I can do this problem. I say this is the velocity vector, Vx, Vy, Vz, relative to us. And I can say the line of sight velocity that I measure is Vx times some angular factors, Vy times some angular factors, Vz times some angular factors. It's just a projection. So if we sit here and we look at stars in this direction, and this direction, and this direction, we're going to see a gradient, apparent gradient in line of sight velocity. But it gets more exciting, right? Because if you can measure this apparent gradient, you could actually solve this equation for these unknowns. We take 3 measurements of V line of sight. We know L, we know B, and we can solve for Vx, Vy, and Vz. Now, you physicists may not appreciate this, but astronomers get very excited about being able to measure 3-space motion because you really can't do it. So this is like you should be jumping up and down and going, yay. So we were really excited about this idea, and we tested it in our simulations. We said, well, how well can we do this? Let's imagine we have a stream coming through in our simulations. Let's observe it. Let's observe 15 stars in it, because that's the order, the size of the data set we've got. And let's ask, how well can we recover the motion? So this is Vx, Vy. The x is the answer in the simulation. And these are giving us our estimates that we came up with from the 15 stars using synthetic observations of this pericentric stream. And this is the other dimensions. And so we have an estimate, and we have errors on the estimate. And you can see that we do fairly well at getting this, although you can see that our error bars are huge. They're hundreds of kilometers per second, right? So on the one hand, this idea works in a way, but it gives you an answer with huge error bars. And the question is this useful at all? And the answer to this question, did I just mess that up? I did, right? The answer to this question, I didn't want to go into it now because I want to get to the end of the talk, but the answer to the question is broadly yes. In our simulations, if we take these estimates with these huge error bars and we integrate orbits, we find that our prediction for where those stars are going to end up at apocenter actually matches where the stars in the simulation end up at apocenter. Not exactly, but in a broad sense. So the last thing I wanted to show you on this section was these are observed stars from one of those pericentric streams that I showed you in Allison's sample. And we've applied this idea to predict what then full space motion is. And we've integrated their orbits here, and this is color-coded with distance. And we're predicting that there should be an apocenter, a cloud of debris associated with these local stars around here on the sky. We do not expect, by the way, this should be a vast overestimate of the distance to this. But however, we can superpose this on this, some data. Dramatic. This is some data I showed you earlier. This is the Hercules Aquila cloud. And there was a suggestive overdensity in the south here associated with the Hercules Aquila cloud. So we tentatively think that this could be, these local streams we see here, could be associated with the Hercules Aquila cloud, which would be really fun because then we'd be connecting debris from one type of survey, velocity locally, to debris from another type of survey on the very largest scales. I do not think this is conclusive at this point. What we're actually doing is going and getting data, velocity data on Hercules Aquila down here, and hopefully we'll be able to do the same thing backwards later on. Okay, so time is getting on. What I told you about is connecting pericentric streams, velocity streams, to clouds. And we're hopeful about this. I don't think we're conclusive about it, but we think that we've got a way of doing this. The bit I'm going to have to miss out is we also think from preliminary data we've got on clouds, we can also, from the data on the clouds, derive the full space motion of the clouds from line-of-sight data alone. And this is recent results. And so our hope is we may actually be able to connect, in the end, clouds on one part of the galaxy to the other. But the bit that I'm missing, so actually I should show you the conclusions from the next section to show you where I was getting to. The end of the next section, what I was trying to get to was this, that we've got these, I told you about the first one, 2 simple geometrical tricks to connect pericentric streams to clouds, and also to say where the clouds themselves were moving. And I think it's fair to say at this point, why is this interesting? I mean, I find a lot of fun in this because you're just using geometry. It feels like I'm an ancient Greek, right? And I'm just using geometry to figure out something kind of fun about how things are working. and simple orbit integration. So I find that fun for itself. But in terms of how does this help us with the big picture? And that's the last thing I want to spend 5 minutes telling you about. And that is, how can this all help us with telling us about the galactic dark matter halo, and by extension, dark matter halos more generally. So for inspiration, the first part is this idea of making connections between stellar debris. And I should be fair, you know, with a stream, you can do this trivially because you can follow a stream. This is actually real observed data from the globular cluster PAL 5. This is a gorgeous stream of stars. The stream is continuous, and you can follow that. So we're already set there. And what I showed you in the middle of the talk is how you can start to do this for not only streams, but also clouds that could potentially be on opposite sides of the galaxy. So that's the first inspiration for what I'm going to tell you. The second is a satellite that isn't flying yet, but it's called Gaia, and it's tremendously exciting for galactic astronomy. So Gaia is an astrometric satellite. It's going to measure positions of stars extremely accurately. Sounds deathly dull, right? But actually what this means is, for the very first time, here we are in the sun with Gaia going around us. For the very first time, we'll be able to measure the distances to stars on galactic scales with great accuracy, and how they move, the proper motions perpendicular to us, which is the holy grail for a lot of astronomy, measuring motions perpendicular to the line of sight. So in the future, we should be able to measure motions perpendicular to the line of sight throughout the galaxy. But the one limitation of Gaia is that, and it's a limitation of this method in general, is even with Gaia accuracy, you can only measure distances to 10% within this circle. That's 10 kpc. Now, I'm interested in things out here. So Gaia is not going to help me with distances, although it helps with proper motions. So the last part of this inspiration was a proposal by Barry Madore and Wendy Friedman that you should be able to find distances to RL Lyras if you calibrate it extremely carefully in the infrared using Spitzer. And you should be able to get 2% distances to individual stars, RL Lyras. And when you start talking about 2% distances to any star in the galaxy here, then you're starting to open up the entire galaxy to saying we can measure full phase space positions in the galaxy. Okay, so that means that you can look at this tidal debris. You can look at X, Y, Z, VX, VY, VZ. You can measure that for stars in these tidal debris. So once you've got all these things together, you can make connections between stars to say they're part of the same debris structure, and you can measure their full phase space positions. What does this mean? The idea is pretty simple. It's actually something I was working on 12 years ago, but it's the recent idea of the RL Lyra distances that have reawakened this. The idea is, if I have full phase space positions observed for debris, it's like I have the endpoint of a simulation. I'm a theorist. That's how I think of it, right? At the endpoint of a simulation like this, of satellite disruption, I have the X, Y, Z, the X, Y, Z positions for everything here. Now, in the simulation, once I have that, I can do anything I want with them. I can integrate them backwards, forwards, whatever I like. So this is an example of running my simulation backwards, which you don't usually do. So I've taken the endpoint of my simulations, and I'm integrating the orbits backwards. Now, in this case, I know the potential of the galaxy, that I run it in. I know the potential of the dark matter halo that I put in. So I put back in the correct potential. And in that case, the stars recombine with the satellite successfully. Okay? Now, in reality, we don't know the potential. And so this might be what happens in reality when I try and do this with real observed data, that the stars in the streams do not recombine with the satellite when I integrate them backwards. And this is a signature that I've got the wrong potential. In other words, this is a signature that I don't understand the dark matter halo of the galaxy. So we can actually use this as a way of testing the shape, the radial profile, and the total mass and extent of the dark matter halo of the galaxy. So we tried this out a little more carefully on simulated debris from the Sagittarius dwarf galaxy. So here's the Sagittarius dwarf in our simulation. This is in the galactic disk, perpendicular to the galactic disk. This is where the sun is, and we observe the Sagittarius dwarf, and we observe streams of stars entirely encircling us, right? So we actually know that there are Alari stars, the type which we know we can get distances to. They've been observed in this region of the stream and in this region of the stream so far, in the red and in the blue in 2 different surveys, right? So we know our Alaris exist here and here. So we can try and get distances to these stars using Spitzer, and these stars using Spitzer, and eventually proper motions from Gaia. And what we actually do is we supplement these samples with some closer RL-iris that we think it will be easy to discover since we know where they should be on the sky. So basically, our proposed Spitzer sample is only 55 stars, and that's limited, of course, because Spitzer is a space observatory. You can only get limited time on it. So our proposed Spitzer sample is only 55 stars from the Sagittarius dwarf galaxy. So what we do is we observe these in our simulations to test how well we can do. So we give them 2% errors in distances. We give them errors in proper motion from Gaia, and we assume some error on the line of sight velocity. And we ask, well, how well can we do? And this is just a simple example. We put them in a potential that had, the dark matter had an axis ratio perpendicular to the disk of 1.4, an axis ratio in the disk plane of about 1.4, that's this big X. And if we bootstrap our errors from our simulated observed sample, you get the sort of error contours that you see here, right? The 1, 2, and 3 sigma level. And so this is saying even with just 55 stars, we should be able to measure the shape of our dark matter halo with fairly good accuracy. And I want to take a moment because, again, you're not reacting correctly. The correct reaction to this is, ooh, because the way this is done in astronomy, if you look at other galaxies, the best way to measure axis ratios, apart from the Milky Way, is using gravitational lensing. And that's really terrific, but what you're measuring then is a projection of the shape of the dark matter halo. You're not measuring the 3-dimensional shape. Here, you're actually going to be able to measure the 3-dimensional shape and orientation of our dark matter halo and measure how fast the dark matter profile falls off. That's an extrapolation from what the simple test I've done here. But this is saying using just 55 stars in one stream. So we have a bit further to go to be absolutely sure, but this is very hopeful in terms of understanding the shape and extent of our dark matter halo, which we like to think that we know from simulations, but it would be a first to actually observe it. So this is a summary of the conclusions. I told you a little bit about streams and clouds and how you can understand their properties with very simple dynamics. I showed you one of these 2 geometrical tricks you can use to measure full space motion from line of sight velocities and how this allows you to make connections between debris. And I told you why this is interesting in the bigger picture beyond being fun for the tiny understanding of debris structures. It's actually a way of measuring the profile, shape, and extent of the only dark matter halo in the universe that we can do this for, and that is the Milky Way's dark matter halo, in 3D, that is. Okay, thanks very much.
Are there more questions for Kathryn? Nick?
A couple of them, but let me start out this. What happens to the dark matter halo that was associated with the dwarf galaxy?
Yeah, that's a great question. So, yeah, what happened to the dark matter halo that's associated with the dwarf galaxy? So it's going to get shredded too. So the simulations I showed you was just particles disrupting, and I didn't distinguish between light and dark matter. So what would, strictly speaking, the extended dark matter halo would get shredded probably first because the stars are buried deep, and then both stars and dark matter would get shredded. And so, for instance, you could take the simulations I showed you and paint the stars to be more concentrated than the dark matter, and then follow just those. But it's not going to affect the general principles of, especially the potential measure, because that's just recombining things, right?
And does the mass of the dark matter particle have anything to do with the way it gets shredded and how it looks?
Well, in the sense that if the mass of the dark matter particle might influence the central density profile of the dwarf galaxies, for instance, and then that could affect how quickly the object is shredded. So that could affect the time evolution. It could affect the time evolution. I don't think it affects the basic ideas of the shape, right? I mean, you would want to know it to affect details, but the shape of the debris is broadly going to be the same.
Follow-up question to that? Sorry,
Yeah.
Does that mean that the dark matter halo is relatively lumpy, lumpier than a smooth profile, or are these just contributing so little mass to the general accretion that you don't expect that?
Right. So you mean from the shredded satellites?
Right. Well, right.
Yes.
I mean, if the halo is built up by
Right.
shredded
Exactly.
events-
Exactly. But the thing is that the satellites that are coming in, the dark matter is much more extended than the light. So when you look in the simulations, the halo is less lumpy than you see in the light because the light starts more concentrated. Now there are dark matter lumps in there from the missing satellites, right?
Yes.
And those can also affect streams, and I've ignored those. So that's a very good point. And I have conveniently forgotten about the missing satellites right now because they're missing, right? So,
I have a couple of questions.
yes.
One, do you
Don't do that, sorry.
are the satellites much less massive than the galaxy?
Yes, the satellites are much less massive than the galaxy. So the sort of thing I'm talking,
What are figures?
1% or less are the
1%.
things. Yes. So the most massive satellite of the Milky Way is the Large Magellanic Cloud, and that's about 1% of the mass of the galaxy. And I'm generally talking about things that are less massive than that. Once you even get up to 1%, you start having to worrying about back reaction. Right. Right.
Another question. On your picture you have shown us, it seems that the distribution of matter in the plane of galaxy is strong and isotropic. Is it correct? So it depends strong on the direction.
Yeah, I'm not sure which part you're referring to.
In one place you have shown a very big concentration of matter, and another no.
Right. So this was when you were looking at the movies.
Yeah.
Okay. So
Not in the movie. In your picture.
Oh, right, the blue one, the blue picture. Is that the one you were thinking of? So in the blue picture of surface brightness, you're not looking at the majority of the mass in the galaxy. You're looking at 1% of the light. 99% is in a disk and a bulge at the center, and the disk is somewhat symmetric, and the bulge is bar-like. So I've been talking about the little fluff around the edge of the galaxy, not the majority of light in the galaxy.
I don't understand. So what is the answer? Is it anisotropic or not?
It's predominantly not anisotropic.
Not anisotropic.
Right.
So why in the picture I see the concentration of
This 1% of the light. You're seeing 1% of the light of the galaxy.
It's only 1%.
Exactly. Yes, I'm not talking about the main galaxy. 1%. Yeah.
Fine, it's a good picture. She's for our representation, just showing what happens to the satellites.
Because you wouldn't see them otherwise, and those were the main thing I was talking about. I should have said that at the beginning.
The stream of dark matter. If we happen to live in a stream of dark matter.
Yes. 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 Yes.
The velocity is
Yes.
higher. When do you expect you will be able to tell us, so people would know?
Yeah, that's a great question. So actually, this was really fun because I put this paper on AstroPH about connecting, and about the same time, Mike Coulin put a paper on precisely this, the high velocity. Did you see that, right? You don't know what I'm talking about. But sorry, you don't know what I took at that paper, right? So I had the exact same thought because he was analyzing a simulation of dark matter halo forming, and he was looking at high velocity streams in the solar neighborhood of dark matter, and here I'm studying high velocity streams of stars. And so actually we're talking about trying to figure out if we can measure, right, if we can get, because I don't think this is very firm yet, if we can say there is a high velocity stream of stars and this is the direction of its motion, it must help you guys, right? So yeah, that's an exciting implication. Debris flow, he was calling this debris flow. I don't know if that term has got out or if it's just Mike calling it that. I don't know.
Maybe one. Oh, Nick has the last question.
So Sagittarius is a very unusual galaxy with a metal-rich population, has very unusual chemical abundances, and it has metal-rich stars. And so if the galaxy is being formed up in the halo of shredded dwarf galaxies, why are there not more metal-rich stars in the halo of the galaxy?
Yeah, so that's a good question.
Better repeat it.
Right. So you were saying Sagittarius contains a lot of metal-rich stars, and
as does the small Magellanic Cloud, as does the large Magellanic Cloud.
right. And so why are there not more metal-rich stars in the halo of our galaxy? So I should point out two things. Well, I'm going to forget the answer to the question by the. Well, never mind. So Sagittarius itself, part of the reason that Steve was so successful at tracing Sagittarius and M giants is because M giants are also metal rich, right, as you know, right? And so they stood out. You got rid of most of the stellar halo and you just were left with these M giants. So Sagittarius makes up maybe a few times 10 to the 7 in light, and a few times 10 to the 7 is in the halo. So that's about a few percent of the stellar halo is contributed by Sagittarius itself, right? But it is a relatively late massive accretion event. So I think the answer why the halo is not the bulk of the halo that we've observed may not be that metal rich is because it may have come from something as large as Sagittarius, but something that hasn't evolved as far as Sagittarius. So it may be less metal rich. But you could get stellar halos conceptually that were more metal rich than ours, which were made from later accretion events.
We see very few metal rich stars in the halo of the galaxy, which means that the objects that fell in and were shredded were missing metal rich objects. And so they couldn't have evolved very long.
Exactly.
So there's a hiatus between the initial shredding of most of them, which produces most of the halo, and Sagittarius.
Absolutely. No, you said it better than I did. That's what I was trying to say. So we think that the accreted part of the stellar halo, the majority of the accretion happened early on, 10 gigayears ago. Sagittarius is an anomaly, and it's contributing a few percent now. It's not the majority.
Post-prerogative here, what sort of accretion events contributed most of the mass of the halo? Were they relatively small things? I mean, much smaller than Sagittarius. Sagittarius must be somewhat large.
No, actually, we think that they were more like an object like Sagittarius, or even a little larger like the LMC, but it was accreted a long time ago.
Okay, so that would dominate the mass.
Right, exactly. So it means that halos can be quite stochastic from one object to another, right? From one galaxy to another, you might have quite different halos. Right.
Okay, well, before we thank Kathryn, I want to remind you she's giving another seminar tomorrow on data point of minorities in science, so please do your email about that. Let's thank her again.
Okay, thanks. Good.
Great. Really